Okay, so in this video, we are going to be talking about gas laws. So we are going to be talking about three gas laws here: Boyle's law, Charles' law, and Gay-Lussac's law. And so we're going to talk about how to use the combined gas law to help you identify each of those individual gas laws. The first one we're going to talk about is Boyle's law. Now, in Boyle's law, the volume of gas is going to change inversely with the pressure of a gas when the temperature is held constant. We're looking at the relationship between volume and pressure when that temperature is constant. And I like this picture, the picture of these three pistons. And so what I'm doing here is as I am pushing that piston down, right, I'm changing the volume of the gas. I'm not changing the amount of gas, I'm not changing the temperature, right? So I'm not making those molecules go any faster, but what I am doing is I am reducing the amount of space that those molecules can move in, and so therefore they're more likely to hit the sides of the container, and that gives us an increase in pressure. When we're talking about Boyle's law, and this is one of the reasons why I like the inverted triangle, is if I'm interested in just Boyle's law, well, Boyle's law involves pressure and volume. And so the equation then for Boyle's law is going to be P1V1 is equal to P2V2. Remember that your temperature is held constant, so that temperature essentially gets factored out of the combined gas law. Okay, so let's do a little bit of Boyle's law practice, and I highly recommend that you set these up sort of the same way we set up the combined gas law problem. And you want to read through and identify exactly what you're looking for. I have a sample of hydrogen gas, and it has a volume of 4 liters and a pressure of 1.0 atmospheres. I want to know the new pressure if the volume is decreased to 2 liters. So what I have here is I have my initial volume, I have my initial pressure, I want to solve for my new pressure, and I have my second volume. Since I'm only focusing here on volume and pressure, I know I'm dealing with Boyle's law. And so I'm going to go ahead and write down my equation. P1V1 is equal to P2V2. And now off to the side, I'm going to go ahead and just make sure I'm good with my variables and what my values. So my initial volume, V1, is 4 liters. My initial pressure is 1 atmosphere. My second volume is 2 liters, and I am solving for my second pressure. So I want to rearrange my equation to solve for P2. So I'm going to divide both sides by V2. I have pressure, P2 is equal to P1 times V1 over V2. Now I could just go ahead and plug my numbers in. So my initial pressure was 1 atmosphere. My initial volume is 4 liters, and my second volume is 2 liters. Now when I go through and I plug everything in, my final pressure is 2 atmospheres. My final answer should have 2 significant figures, since all my measured values have 2 significant figures. Next up is Charles' law. Charles' law basically says that the temperature in Kelvin and the volume of a gas are directly related when the pressure is held constant. Looking at Charles' law, I love this inverted triangle. The C is right next to the volume and the temperature. I know they're directly related, and I know that in this case I am not dealing with pressure, right? So pressure will cancel out. And the equation for Charles' law is V1 over T1 is equal to V2 over T2. And so what's happening here, and again, I've got these pictures with the pistons. As I am taking my sample of gas that is in a container, and let's say I have a flexible container like this piston, as I heat this up, that gas is going to expand. As those particles are heated up, they are going to move faster and faster, and so they are going to expand in order to keep that pressure constant. Charles' law practice. In this example, we have a sample of gas that occupies 6.8 liters at 327 degrees Celsius, and I want to know what the volume will be when it's cooled to 27 degrees Celsius. So let's go through and identify all my pieces. 6.8 is my initial volume. My initial temperature is 327 degrees Celsius. I want to know my new volume when I have reached my new temperature. All right, so let me go ahead and write out our equation. V1 over T1 is equal to V2 over T2. And then again, I do really like to write out my variables, just helps me keep things straight. So I know that V1 is equal to 6.8 liters. T1 is 327 degrees Celsius, but remember, with every gas law, I have to make sure that that temperature is in terms of Kelvin. And so when I convert this to Kelvin, it is 600 Kelvin. Notice I put the decimal place after the last zero. I want to make sure that I have the correct number of decimal places for this value. All right, I'm solving for V2, and T2 is equal to 27 degrees Celsius, but again, I have to go ahead and convert that to Kelvin, and that is 300 Kelvin. All right, so now it's a matter of rearranging my equation to solve for V2. So I'm going to multiply both sides by T2. Right, so T2 will cancel. And so V2 is going to be equal to V1 T2 over T1. I just want to go ahead and plug my numbers in. So I have 6.8 liters times 300 Kelvin over 600 Kelvin. And that is going to equal 3.4 liters. I am only allowed to keep two significant figures in the end because 6.8 only has two significant figures. All right, so the last law we're going to take a look at here is Gay-Lussac's law, and this says that the pressure is directly related to the temperature in Kelvin when the volume is constant. I'm holding my volume constant. My equation for this is going to be P1 over T1 is equal to P2 over T2. Again, I love this inverted triangle. It is right here, right next to the G, right next to Gay-Lussac's law is pressure over temperature. Again, I've got these cylinders here, and as I move from the cylinder on the left to the cylinder on the right, so you can see I'm heating this cylinder here on the right, as I am adding heat, I'm raising the temperature, I am making those molecules move faster. They move faster, there are going to be more collisions with the wall as opposed to at a cooler temperature where those molecules are moving a bit more slowly. You're going to have less collisions with the wall. We're going to do an example of Gay-Lussac's law. We'll go ahead and read it and then identify all the pieces. So the gas left in a used aerosol can has a pressure of 3.6 atmospheres at 27 degrees Celsius. If the can was thrown into a fire, which is a terrible idea, don't ever do that, what is the pressure of the gas at 927 degrees Celsius? All right, so let's identify all of our pieces. 3.6 atmospheres is our initial pressure. 27 degrees Celsius is our initial temperature, that would be T1. I want to know the final pressure, so I'm going to be looking for P2 after the can has been heated up to 927 degrees Celsius. All right, so let's go ahead and write out our equation. So P1 over T1 is equal to P2 over T2. I really like to write out all of my variables. So P1 is 3.6 atmosphere. T1 is 27 degrees Celsius. Remember that has to be converted into Kelvin, so that's going to be 300 Kelvin. Make sure you include that decimal place after the 0. T2 is 927 degrees Celsius, and again I want to make sure I convert that. That's going to be 1200 Kelvin, and again make sure you include that decimal place. And then P2 is what I am looking for. All right, so I'm going to go ahead and rearrange my equation to solve for T2. So I'm going to multiply both sides. I'm sorry, I'm solving for P2. So I'm going to multiply both sides by T2. And so what I have here is P1 times T2 over T1 is equal to P2. Now let's go ahead and plug all of my values in. So it's 3.6 atmospheres times 1200 Kelvin, all divided by 300 Kelvin. When I plug all of my values in, I get 14 atmospheres. I'm only allowed to keep 2 significant figures because of the 3.6 atmospheres. That only has 2 significant figures.